Sponsored by the Fire Research Group. This seminar, as those of you who've joined us last semester and this semester know, is organized by Michael Gollner from UC Berkeley, Crystal Colden from UC Merced, and myself, Janet Goyan Iniguez, also from UC Merced. Today, we're pleased to be welcoming our speaker, Dr. Park Williams. And before I introduce the speaker and before we begin, I would like to make a series of announcements as far as logistics for the webinar and the discussion that we're going to have after. So the seminar will take place during the first hour of our seminar. During this hour, participants are able to ask questions through the Q&A box on Zoom. So we do ask you to use that versus the comment on the Zoom interface, the chat box rather. So questions will be answered right at the end of the presentation in the order that they are received in this Q&A box. Following the talk, we'll be hosting an extended hour of discussion. Everyone is invited to attend and discuss. Students and early career folks are highly encouraged to join us. And a link to the discussion section will be posted in the chat. And with that a series of announcements, allow me to introduce our speaker for today. Our speaker, Park Williams, studies the climatological causes of change in water distribution across the continents and the effects of the changes on life. He is an associate research professor at Columbia University and will begin an associate professor position in UCLA's Department of Geography this March. And with that, Park, the floor is yours.
Great. Thank you, Jeanette. Thank you, everybody, for attending this. I'm really excited to be able to give this talk on Western United States wildfire, especially because next week my family and I will be returning to the Western U.S. I'm from California's Central Valley and have now been away from California for a decade, and my research has continued to gravitate to the Western U.S. It's really exciting to be moving back to the region for that reason, as well as to be within actual striking distance of many of you on the call, who will be hopeful friends and collaborators once I get there. It's also been a bit strange studying the Western U.S. and especially in the last several years when wildfire has been so intense, all the way from the cool and wet east, which has been abnormally wet for the last several years. And so if I'm going to be studying these wildfires, it would only be fair, I think, for me to be in the smokes path when they really get going. This picture that I'm showing is of a very intense day of smoke, September 9th, 2020, and that fire season in the West was exceptional throughout. Here's a map of just the distribution of wildfire events going on a single day in September. And up until mid-August, it was still really unknown whether it was going to be a severe wildfire season. Things were definitely dry, but it takes a lot more than just dryness to create actual intense wildfire conditions. And then the wildfire season really got kicked off immediately in mid-August when a burst of lightning strikes over the course of a few days took place. A tropical storm Fausto came up the Pacific coast from Mexico and created lightning strikes across much of California, especially Northern California, in the Coast Range and in the Sierra Nevada. And that on its own was an exceptionally rare event. If you live in California, you know that lightning is pretty rare, especially on the coast. And that exceptionally rare event coincided with another very rare event, and that was a record-breaking heat wave. This map here is showing locations where daytime high temperatures set records on set daily records sometime in August. And that convergence of moist air coming from Mexico and creating a lightning storm coincided exactly with the timing of this intense heat wave. And so the availability of sparks converging with record-breaking heat was the perfect recipe for wildfire. And then in August, there was a second very intense and prolonged heat wave. This heat wave causing temperatures to go above 110 in coastal California, which in my experience in California is really unheard of. If prior to 2020, somebody would have asked me, will Paso Robles hit 112 this year? I would have said definitely not. Maybe low hundreds is what Paso Robles is capable of, especially because Southern California had actually a wet winter in winter 2019, 2020. And with soils being abnormally wet going into summer in Southern California, you'd expect the wet soils to be able to absorb some of the heat delivered by a heat wave. And so it is actually kind of scary to think what temperatures in Southern California would have done had winter 2019, 2020 actually been dry. There were some exceptional fires that occurred in this exceptional fire season. One was the Creek Fire. One thing that really got my attention beyond just the pictures that make it look like a nuclear weapon had been detonated is this rate of spread where during a 24-hour period, the Creek Fire was spreading at a rate of about 1 football field every every 2.5 seconds. That's really fast, but wildfires do get faster. The Camp Fire that burned in Paradise, California, a couple years ago actually spread during the first half hour or so of that fire at a rate of 7 football fields per second. The rates of spread of wildfires always blow me away. Many people have been impacted by wildfires in recent years. Of course, many have been directly impacted by having to evacuate, but even people living far away from wildfires have been affected via the smoke. And the events of 2020, while they seem so extreme, are really part of, and I should say the events of 2020 in California that seem so extreme are really part of something larger going on. The annual area burned every year has risen dramatically over the last 35 or more years. This plot is showing the annual total area burned by wildfires in all of the Western United States. So not just California, but the entire West. And you can see that since 1984, there's been about a 300% increase in the annual area burned. This is a single time series, and so it looks pretty simple, but it actually comes from quite a bit of effort. My graduate student, Caroline Zhuang, who's doing really awesome work, and I've been working on putting together a database of Western US wildfires going back to 1984. This database includes Landsat-based satellite measurements of burned area that have been put together by the US Forest Service's MTBS project. And then we supplemented that with a bunch of smaller fires that have been recorded by the federal government. These are fires that required suppression efforts, or at least use suppression efforts, and so there are records of those. And then that data set comes through 2018, and I've extended through 2020 using the MODIS satellite-derived burned area product. So 2020 was by far a record-breaking burned area year, at least in terms of the modern records, which we can say started about 40 years ago. And in California, that was even more so. 2020 actually makes the rest of the record look flat, coming in with a burned area about 3 times higher than the previous record, which is 2018. But prior to 2020, that previous record still had a really strong trend. It's kind of hard to see here because 2020 dwarfs everything. But before that, studies were being carried out, including by me, trying to diagnose the drivers of the large observed increase in burned area through 2019. So in this talk, I'm going to be working to diagnose the drivers of the increase in area burned in California and the Western US. But I want to be careful to not just imply automatically this increase in area burned is a bad thing. When we read in the media or hear from politicians about the wildfire, then it's generally presented as a bad thing. But an increase in burned area isn't necessarily on its own automatically a bad thing, because wildfire is, of course, a natural process that has been going on for millions of years across the continents, for as long as plants have been on the continents. And if you take a walk through any old growth forest in the Western United States, then you will see ancient fire scars embedded in the tree trunks. And many tree trunks contain many fire scars. We can actually use tree rings to detect the exact year of individual fires. And sometimes we can actually tell even the time of the year, the season when the fires occurred. And tree ring fire scars tell us that prior to interference or large-scale suppression efforts by European Americans in the late 1800s, early 1900s, wildfire was extremely common across a lot of the Western US. And so a return to common wildfire isn't inherently a bad thing for everything. It isn't inherently a bad thing for ecosystems. And I'll show later that over the millennia, there have been changes from centuries with a lot of fire to centuries with not so much fire. And those changes weren't inherently a bad thing. But this increase in wildfire activity has been perceived as a bad thing by people, and I'd say for pretty good reason, because we find ourselves increasingly in the way of these fires. We live in areas that are burning increasingly frequently, and we're seeing an increasing frequency of large populations being displaced temporarily or even permanently because wildfires are burning through the communities they're living in. Even for a person not living in one of these communities that's in high fire danger, really there's really not a single person in the West has not been affected because wildfires emit huge amounts of harmful pollutants. And so people generally have a negative reaction to fire because they are impacted negatively. Even ecosystems, though, may not be appreciating the recent increase in wildfire activity. The recent increase in wildfire activity has coincided with an increase in the areas with stand replacing crown fire in some areas where those fires were not so common, probably in a natural pre-suppression world. This picture here is is in the footprint of the Las Conchas fire that occurred in 2011. This is a ponderosa pine forest, and ponderosa pine forests in the southwestern United States naturally have undergone in the past a high frequency of low severity fires. That is, fires burn through the understory of these forests very frequently, say every 5 to 15 years in many of these areas, keeping forests from ever getting too dense to carry stand replacing crown fires. And recently we've seen an increase in the size of stand replacing crown fires. It'll likely be many hundreds of years before this wildfire footprint will be repopulated by ponderosa pines, if ponderosa pines can repopulate at all. They just don't spread all that quickly. And regardless of whether we think wildfire is a good thing or not, it's clear that we as a society have agreed that it really isn't a good thing. As wildfire has been increasing rapidly over the last 4 decades, then our expenditures on trying to put out fires have increased in step. From this time series alone, it's clear that our policy of continuing to try and put out wildfires is continuing unabated, even though we may realize that it's not such a sustainable idea. And I'll talk a little more about that in a bit. And so what this plot is telling me is that we have really, in the last 40 years or so, lost control of the Western United States wildfire regime, and especially in forests. I'll show that in a little bit. Throughout much of the 20th century, we were very successful at putting out wildfires. But over the last 40 years, despite our continued effort to do so, wildfires are increasingly escaping our control. And so for the rest of this talk, I'm going to work our way through the drivers of wildfire and try and diagnose why we've seen this increase in wildfire over the last few decades. And so we'll start by looking at the main ingredients that are required for fire. Every large wildfire really needs 4 switches to be on in order to really get going. And those 4 switches are fuels. So you need enough vegetation in order to be able to carry a large fire. In order to grow enough vegetation to do so, you need moisture. And so moisture is actually, and perhaps counterintuitively, one of the main ingredients for fire. You need enough moisture to grow fuels. But then you need a spell of aridity to occur. That is, you need for some amount of time the environment to become abnormally dry. You need the atmosphere and precipitation to team up to dry out this abundant vegetation in order to in order to allow abundant vegetation to be flammable enough to carry large fires. And then of course you need an ignition from lightning or ignition from humans, whether intentional or on accident. And then finally, once all these switches are on, then you generally need strong winds in order to carry fire long distances and spread quickly. So we're going to start by looking um, at fuels, at vegetation. And we can begin this discussion by considering two extremely different landscapes. On the left, we have a lush forest where fuels are really not a limiting factor. Instead, what's a limiting factor is aridity. You can see this is a wet environment. And so in most years, this lush forest is not going to stand a chance of burning because it's too wet to burn. But occasionally a severe drought year may occur, or a severe heat wave may occur, drying out fuels and allowing this abundant this fuel abundant landscape to burn. And so on the left, we would say that this landscape, the fire regime in this landscape is limited by aridity, and it's not so much limited by fuels. On the right, we see the exact opposite. We see that there are not many fuels here, and instead it's really dry. Probably it's dry enough every year to dry fuels out to allow them to be flammable, but the reason we don't see a ton of wildfire activity in this desert environment is because there's simply not enough fuel. And so in this landscape, we'd say the wildfire is not limited by aridity, it's instead limited by fuels. And so now let's look at the burned areas in two different components of the landscape. On the left, we're looking at the trend in annual area burned in forested areas. And on the right, we're looking at the trend in annual area burned in non-forested areas. This is there's of course many different land cover types, and this is a very brute way of breaking things up. But we can see very clearly here that the increase in wildfire activity in the Western United States is dominated by the increase in forest fire. In areas where fuel is more of a limiting factor, we don't see an increase in burned area nearly as strong, although we do still see some of an increase. Zooming into California, because this is a California fire science seminar, we see a similar story playing out. We see that California's increase in wildfire is really being dominated by forest fire. And so here we are really seeing, I think, we should be having impressed upon us the importance of fuels in the story of Western United States burned area trends. And that story is really interesting. It turns out that if we look at paleo records, we can learn about the long-term history of fire rather than just looking at the last 40 years. And we see something really interesting here. Lakes across Western North America have been collecting evidence of wildfires for millennia. Naturally occurring lakes have been sitting there as basically collectors of ash and charcoal. And when ash and charcoal fall into lakes or wash into lakes, then they're deposited on the lake floor in sequential order. And so today, if we stick a tube into the mud at the bottom of a lake and pull that tube out, then we have preserved in the lake floor in order a record of wildfire activity. And scientists have now done this from lakes across the western side of our continent, or across the entire continent, in fact. And what they see is something very interesting. They see that over the last 1,400 years, Western United States wildfire activity has varied greatly. There have been some centuries when wildfire activity was relatively modest, and there were other centuries when wildfire activity was really, really active. And scientists have then compared those records from lake sediments to tree ring records of drought. And what they see is over the last 1,400 years, drought and Western US wildfire activity have varied hand in hand. The cool, wet years or centuries were the centuries when there was not much wildfire activity, and the warm, dry centuries were centuries when there was much more wildfire activity. And then in the late 1800s, this very tight relationship became totally unhinged, where tree ring records indicate that over the last century, conditions have become even drier and more conducive, they have drifted in a direction that should be more conducive for wildfire. But the lake sediment records and also tree ring records that contain fire scars indicate that wildfire activity essentially plummeted and disappeared from the landscape over the last century or so. Scientists have described the result of this as a wildfire deficit. Climate says there should be more fire, but instead there's less. And as a result of our fire suppression activities over the last century, some or many forested ecosystems have become artificially dense with vegetation. And no picture that I have ever found illustrates that more clearly than this pair of pictures from Yosemite that are 112 years apart. In the late 1800s, this landscape had a much sparser forest than it does today. That sparser forest was maintained undoubtedly by regular returns of wildfires that kept some areas from becoming forested at all, and kept many forested areas from not being so dense. But after a century of successful wildfire suppression, then this ecosystem has much more available to burn. And so a very logical conclusion would be that many forested ecosystems in the Western United States are now prone to having large wildfires escaping our control in a way that they were not a century ago, simply because of an increase in fuel abundance. Even if climate change had not been occurring, we'd expect wildfires in many Western United States forests to more easily escape our control. But that fire deficit narrative doesn't apply everywhere, and I think that oftentimes it's overly used as a blanket explanation for what's going on. This plot is showing the trend in burned area in national wilderness areas. In national wilderness areas, we don't work nearly as hard to fight fire. These are supposed to be natural areas where nature is allowed to carry on as if we didn't exist to whatever degree is possible. And so when lightning wildfires strike in, or lightning-induced wildfires begin in national wilderness areas, we generally don't put them out. In these wilderness areas, we still see a strong trend toward increasing wildfire. Additionally, this fire deficit narrative is most applicable to the drier forests in the southwestern United States, where wildfire was historically, prior to our interference, a very regular thing. So a century of wildfire suppression has very likely had a much larger effect in the southwestern forest, where fire was historically very frequent, than it would in a wet, dense forest in the northern Rockies or western Cascades, where fires would have only occurred every 1 to 3 centuries anyway. That meaning that fire suppression efforts probably haven't rearranged the structure of those forests nearly as much. And yet in the dense forests of the northern Rockies and Cascades, we still see strong increases in burned areas. So fire suppression has very likely loaded the dice toward encouraging large wildfires in forests in the Western United States, but that narrative does not apply everywhere. And it's possible that even in the southwestern forests where that narrative does apply, that there are other things also promoting the increase in forest fire activity. And so that's the section I'll go into now, talking about aridity. And the point that I'm going to try and make is that I think oftentimes when there's a discussion or when there's an effort to quickly describe a diagnosis for the increase in forest area burned, a false dichotomy ends up developing where it's either said that forest management is clearly the culprit here, or that forest management is no big deal and instead climate change is clearly the culprit. But I'm going to show you evidence that that tells me that I think that both things are likely to be occurring. And we've already seen evidence of that. The paleo record that I showed you of the charcoal sediments in the bottoms of lakes indicate that climate has always been a big driver of year to year or century to century changes in wildfire activity in the Western United States. So if there has been a climate change over the last 40 years, why wouldn't it have also been important the same way that it was over previous centuries and millennia? So the first variable that we're going to look at in diagnosing the role of climate in burned area is a variable that I refer to as the summertime fuel dryness. This is a calculation that relies on observed climate data, and the calculation is really of the fuel moisture of dead logs. These are logs that respond to changes in the moisture balance of the environment on the order of 1 to 2 months. And in this plot, we're looking at a time series of summertime fuel moisture in Western United States forested areas from 1984 through 2020. And you can see a trend toward more positive. That means a trend toward drier conditions. The 80s and 90s, fuels were abnormally wet. And in the 2000s, fuels in most years have been abnormally dry. And we can compare this record to record of Western United States forest fire area. That's what's now shown in green here. And just by eye, we can see there's a relationship where wildfire area or forest fire area was lower in the years with high fuel moisture or low fuel dryness, and burned areas were higher in the years with more fuel dryness. A better way of visualizing this relationship and quantifying the strength of this relationship is through a scatter plot. In this scatter plot, every dot represents a year from 1984 through 2020. On the x-axis, we're looking at fuel dryness. So as we move right along the x-axis, we're looking at years that were drier and drier. And those years that are drier correspond with more burned area. That's what's shown on the x-axis or on the y-axis. And the years that were wetter had less burned area. And you can see this relationship is quite strong. Not only is the relationship quite strong from year to year, but it's also strong from decade to decade, or comparing two chunks of about 20 years. The blue dots represent years before 2000, and the red dots represent years after 2000. And what we can see is that because the 2000s were drier than the 1900s during this study period, then the burned areas were much higher, or at least this is such a strong correlation that it's very difficult to see a way that this relationship could emerge without being causal. This relationship gets even stronger if we look at another variable, and this variable is called the vapor pressure deficit. And the vapor pressure deficit is essentially the thirst or the sponginess of the atmosphere. Technically, it's the difference between the amount of water vapor that is in the atmosphere, that is humidity, and the amount of water vapor the atmosphere could possibly hold. And that's called the saturation vapor pressure, and that's dictated by temperature. And we can see that when we look at the vapor pressure deficit, especially during March through December, then we see a very strong relationship with the annual forest area burned in the Western United States, accounting for 82% of the variability in this plot. And once again, we see the more recent warmer and drier years coinciding with more burned areas. And the clustering of the blue 1900s dots to the bottom left and the red 2000s dots to the top right indicate that not only is this relationship really strong on the year-to-year time scale, but very likely the warming and the drying of the forest environment in the Western United States over the last 4 decades is responsible for a good amount of the increase in forest area burned. But here's kind of a complicating factor. Here, I'm making the point that that burned areas strongly respond to atmospheric aridity. That is the demand that the atmosphere has for moisture, which is strongly dictated by temperature. But of course, precipitation must also be a really important part of the recipe. Precipitation is, of course, the source of fuel moisture, and a study published in 2018 by Zach Holden and others pointed out that the correlation is also really strong between the annual acreage burned in forested areas and the frequency of wet days, especially during summertime. That correlation is tops out my analysis when we look at wet days between May through September. And Holden and others defined the wet days as days when more than 1/10 of an inch of precipitation, or 2.54 millimeters, falls. And so if we look at the annual frequency of wet days, we see that indeed it does have a strong correlation with burned area, and that there has been a trend from the 1900s to the 2000s toward there being less wet days per summer, and that trend has coincided with an increase in burned area. Notably, the correlation is stronger when we look at the correlation with the atmosphere's vapor pressure deficit, but both of these correlations are strong. And the reason why I say that there's some confusion that gets added here is because it is very likely that it's not the case that just one of these variables is the dominant driver and not the other. But that's really hard to actually discern, because these two variables, the atmosphere's vapor pressure deficit and the annual frequency of wet days, are highly correlated with each other. When you have a lot of wet days, and that is going to coincide with more cloud shading, with more evaporative cooling, and that causes temperatures to be cool. So there's some interesting land atmosphere interactions that go on. And ultimately, it makes it very difficult to figure out which one of these is really the dominant one, or what share of the change in burned area do both of these variables deserve. We can get more of a sense for whether or not this is just a fluke that the vapor pressure deficit correlation is so strong if we break the Western United States into different regions. And so that's what I do here. And here I just look at 3 major river basins. I look at river basins in the Sierra Nevada mountains. I look at the Upper Colorado River Basin, and I look at the Columbia River Basin. And in each of these river basins, I compare the annual forest area burned in that basin to vapor pressure deficit on the left scatter plot and the frequency of wet days on the right scatter plot. And in each scatter plot, I show the predictive variable during the range of months when the correlation is optimized. And in each case, we see that the correlation is stronger with vapor pressure deficit than it is with wet days. Now, that doesn't mean that it really is vapor pressure deficit that is the king driver of burned area and the wet days don't matter. But it does mean that very likely vapor pressure deficit does have its own unique contribution to burned area. And it's not arising just because of coincidence in the fact that vapor pressure deficit has a strong correlation with wet days. So here I've tried to make the point that it appears that trends in climate are largely responsible for the increase in burned area in forests in the Western United States. So does that contradict the point that I made earlier in the presentation, where I indicated that an increase in forest density due to fire suppression over the last century has likely been a contributing factor to the increase in forest fire area in the Western United States? No, I don't think so. I don't think that it's an either or. I think both things have been important. And I try and illustrate that point here, where on the right, I'm showing you the same analysis that I've been showing the last several slides. This is the forest fire area versus the vapor pressure deficit, and we see this really strong relationship. Over here, if we look at non-forested areas, we see this relationship break down. I've accidentally mislabeled this y-axis forest fire area, but this is actually non-forest fire area. And we see when we step outside of forests, remember, forests are areas where fuels are most abundant, and therefore the fuels are going to be not so much of a limiting factor in preventing fire during a very warm and dry year. Non-forest, on the other hand, is composed of many different things, but largely grassland and shrubland, where fuels are more of a limiting factor. And therefore, the fuel switch isn't always turned on, even if the aridity switch is. You can see when we jump into this less fuel-dominated, these more lightly vegetated ecosystems, then this correlation breaks down. And just with these two plots, I think that we see a really important implication. That is, as you add fuels to an ecosystem, then you seem to see an increase in the ability for wildfires to respond to climate. And so it makes sense to me to make the assumption that if we increase the fuel abundance within a forest, then we very likely see a stronger correlation between aridity and burned area than we would if that forest was not artificially stocked with vegetation because of a century of fire suppression. That said, it's pretty tough to see much of a difference here in the relationship between VPD, the vapor pressure deficit, and forest fire area in the first 20 years or first 15 years of this this analysis versus the more recent 2000s years. And if fire suppression was artificially increasing the abundance of fuels, we might expect this relationship to have become tighter over time, but we don't see a whole lot of evidence for that. So I do think that fire suppression has artificially stocked many Western US forests with fuels that have increased the ability of warming and drying to increase forest fire area. But at the scale of the Western US, it doesn't appear that process has been so fast as to have caused the skyrocket in burned area in the last 40 years, but more that in general, if forests had as much fuels as they did a century ago, then we probably wouldn't have seen the same increase in burned area over the last 40 years due to climate change as we have in the real world. And so far, all this discussion has just been about fuels or aridity, but ignitions are, of course, the first ingredient that you really need for a fire. And humans are a very important source of ignitions across the United States. In the Western US, humans are responsible for about half of the wildfires that occur. And they are responsible for essentially all wildfires that occur outside of summertime. Lightning is predominantly a summertime phenomenon. And so when we see fires occurring in the spring and in the fall in the Western US, then those are usually caused by humans. And like I said earlier, in California, there's not much lightning that occurs at all. And the vast majority of fires are set by humans or caused by humans, so caused by human infrastructure, such as power lines. And over the last, or during our study period, and specifically this data set on population covers 1990 to 2010, there's been a marked increase in human population. The population of the Western United States increased by 36% between 1990 and 2010, and that increase was even more rapid, or the relative increase is even more rapid in so-called wildland urban interface areas. These are areas where human communities and ecological communities, vegetated communities are coinciding, and people are living in areas that are sometimes or regularly really flammable. And so this sets up for a straightforward hypothesis: with more people on the landscape, and especially in vegetated landscapes in the Western US, then we should expect that ignitions have become less of a limiting factor. And if that's the case, then perhaps we should see that not only has burned area gone up, but the frequency of large wildfires has gone up. But we actually don't see that. Here's a time series of the annual count of large wildfires. In this case, I'm considering large wildfires to be wildfires larger than 100 hectares, or about 200 football fields. And wildfires larger than 100 hectares make up something like 95% of the total area burned in the Western US. What we see, though, is that even though human population has increased by 36% during our study period and has risen even faster in flammable areas, we have not seen an increase in the frequency of large wildfires. Now, this is, of course, a result that is only possible to see when we zoom out at the scale of the Western United States. There are certainly many individual fires that would have never occurred if it were not for people living in the wildland urban interface or near flammable ecosystems. Another question is, even though the frequency of area burned has gone up, is it possible that the trend in the, even though the frequency of large wildfires has not increased as human populations increased, perhaps the constant rolling of the dice with human ignited fires and the increase in human in human population has allowed for fires to become larger in areas where, in vegetated areas where humans have moved into during the study period. And so in this case, or to test this, I found all of the forested areas where the wildland urban interface encroached into the forest area during between 1990 and 2010. And specifically, I found forested areas, those are shown in blue in the map, where forested areas that were not within 5 kilometers of the nearest wildland urban interface in 1990, but by 2010, they were within 5 kilometers of the wildland urban interface. And then for each of those areas, I found a nearby forested area, so a forested area that experiences similar climate. And I found a nearby forested area that remained at least 5 kilometers away from the wildland urban interface throughout the entire 1990 to 2010 period. And what we see is that the trend in burned areas has been nearly equal in both zones. And so it doesn't appear from this analysis that changes in human population have really in the last 30 to 40 years have really played a big role in explaining the increase in burned area. Now, certainly, if people would have never lived in the Western United States at all, then the amount of fires that occur and the area burned in a given year would be dramatically different. But given the world that we inherited, the change in human population over the last 40 years doesn't seem to have been a giant driver of increases in area burned at the scale of the Western United States. It's also very interesting to look at the trends in total area burned by ignition type. These analyses that I'm showing on this slide are a bit shorter. They are covering just 1992 to 2017, and that's because this data set that's provided by Karen Short of the U.S. Forest Service specifically diagnoses or provides the cause of each fire, and that is not available for the longer fire data sets that I've used. On the left, we're looking at trends in burned area in total burned area for the Western US. On the right, we're looking at forest fire area only. And in both cases, we see that the increase in burned area, and especially in forest fire area on the right, is actually dominated by fires that were ignited by lightning. The increase in burned area is also strong for fires ignited by humans, but not nearly as strong. And so this is kind of the final nail in the coffin to me that says that human ignitions, while of course important to the large scale fire regime of the Western United States, have not really been that important in driving the increase in burned area in the last few decades. Now, finally, I'll wrap up by talking a little bit about climate change and why climate trends in the future are likely to have such a strong influence on burned areas going forward. In all of the scatter plots that I showed so far, I took the approach that's shown here on the left, where the record of area burned is actually expressed on a log scale. That means that the values on the y-axis are actually increasing exponentially. And the reason I do that is because that is a way to really show that the relationship really is strong and appears to have been stable over the past 4 decades. But if we take the y-axis off of the log scale and express the y-axis in its native units, then we see that this relationship is actually, or has been so far, quite exponential. What that means is that every bit of warming and drying that's occurred over the last 4 decades has caused a larger increase in forest area burned than the previous bit of warming and drying that occurred. And the implication related to climate change is huge, because if we continue to nudge our way toward warmer and dry conditions by moving right along the scatter plot, then we quickly have forest fire areas completely blow up to actually totally unrealistic numbers. At some point, very quickly, we run out of forest. And so we don't expect this relationship to stay stable over the long term, say over the entire century. At some point, forest fires get so large that they become limiters of themselves. They begin consuming so much fuel that forest fires have to begin reducing in size. But that implication indicates that we are really in for, I believe, quite a change in what forest ecosystems and fire danger in many human communities looks like in the coming decades. But the pace of that change is really going to be set by what I was talking about earlier, and that is what really is more important. What is the dominant driver of the increase in area burned? Is it vapor pressure deficit, or is it the frequency of precipitation? In these plots, I'm plotting in black the observed record of both. On the left, we're looking at the observed record of March through December vapor pressure deficit, which correlated so strongly with annual forest area burned. On the right, we're looking at observed wet day frequency, and you can see this trend toward a reduction in the frequency of wet days during summertime in Western United States forests has really been something specific to the last 40 years. But if we look over the last 70 years, then we actually don't see much of a trend. Underneath these records of observed climate are records of climate simulated by the latest version of climate models that were participating in the recent CMIP-6 experiments. And these experiments are run to investigate how climate change is likely to change in the future. And these experiments are run with a range of scenarios. In this case, I'm just picking two scenarios. One scenario shown in blue is a scenario where in the next few decades, we as a globe really strongly curb our greenhouse gas emissions. And then the red scenario is a scenario where we continue burning greenhouse gases at a really high rate. But both of these scenarios have considered for vapor pressure deficit, 34 different models that had all the climate data I needed. And for each model, I just took one simulation per year. And what you can see is that the trends that we've experienced so far in the real world agree well with the trends that we experience that have been projected or simulated to occur due to greenhouse gas accumulation in the atmosphere so far, but that the future trends are going to be really strongly dictated. The future trends in vapor pressure deficit are going to be really strongly dictated by what we as a globe continue to do with our greenhouse gas emissions. Then on the right, I do the same thing with daily simulations of precipitation from 32 models participating in these CMIP-6 experiments. And what we can see is that over the long term, we do expect human-caused climate change to cause a reduction in summertime frequency of wet days. That should continue to promote the frequency of big wildfire years. But we can also see the trend in wet days that we've seen over the last 40 years is much larger than that simulated to occur due to climate change, suggesting that much of the trend that we've seen in the last 40 years has been natural and may reverse in the coming decades. At the same time, the climate models are suggesting that even though the average, long-term average in wet day frequency is not projected to change all that much, the range of variability is. And so the frequency of very, very dry summers is projected to increase quite a bit in both of these emission scenarios. And so the first conclusion from both of these plots is that both of these climate variables are projected to trend in directions that are consistent with more very large wildfire years. And because the response of forest fire area to both of these climate variables is exponential, it indicates that we are very likely to see not small increases in burned area in the coming decades, but continued very large rapid increases in burned area. But the exact pace of those increases in burned area is really going to be dictated by nuanced questions about which of these is really the more important variable. Further, at some point after burned areas continue or keep accumulating, then fire should become more self-regulating. And an important question is, when will that begin to occur? And so in this talk I've tried to use data to address a question that is often discussed in media and in politics as being overly simple with a false dichotomy, where it's either forest management or it is climate change, or sometimes people blame the increase in human population. But it's more complicated than that. Here I want to just finish with a clip just to demonstrate to you how information about climate change and forest fire in the Western US is making its way to the highest levels of decision making in Western United States, or in the United States government.
Many people have suggested that a big part of the problem in California wildfires is the lack of forest management. The fact that there's so much debris underneath the trees that fuels the intensity of the fire. Mr. Curry made the statement that most of that land's federal land, so there are a lot of rules and regulations that prevent forest management. I just wanted to know your thoughts on that.
Well, I've heard one of my clients, who's a emergency manager for a regional power provider, went out to California to consult with Pacific Gas and Electric after all that. And, you know, he said, you know, the whole state is a tinderbox. I mean, you can't remove any, even if a tree falls over and dies, you can't remove it. So all of that fuel builds up, and of course it's gonna blow. Okay, so there must be some regulations that can be changed so all that can be cleared out. I also, when I announced that I was testifying in this hearing, I got emails from several firefighters in California who emailed me and said, tell them it's not climate change, it's these crazy regulations allowing people to build houses where they shouldn't, allowing all this wood to build up. We need to do something. I mean, blaming this on climate change is just sort of wasting everybody's time and trying to deal with this.
And so here we have a lifelong climate scientist relying on anecdote to promote a narrative that I think has this very false dichotomy where it could either be climate change or it could be failed forest management, but there's no way that both things are actually interacting. In this talk, I have attempted to use actual data to indicate that the story is actually much more interesting and complex. I showed that video specifically with graduate students in mind. Graduate students are told all the time they need to keep up with the literature. I also recommend keeping up with these Senate and congressional hearings on climate change. They are excellent viewing, and despite all that we learn in the scientific literature, it's important to be reminded of where the forefront of knowledge is in the actual decision-making rooms and the questions that still need answering and clear answering for the people who are making decisions. The conclusion of my talk is that it appears that in the Western United States, we're in a real pickle. In a lot of forests, we have been suppressing fire for the last century, and that has allowed for an accumulation of fuels, causing forest fire area to become less limited by fuels and allowing forest fire area to be more limited by aridity. As aridity has increased over the last 50 years or so, then we've seen forest fire area increase very strongly. As forest fire area has increased very strongly, we have doubled down on our policy of fighting essentially every fire as hard as we can. Because we were good at that for so long, we have a lot of people living in flammable parts of the Western United States that are now in far more danger than they were 50 or 100 years ago when conditions were much less arid. As we continue to fight fires essentially as hard as we can, we continue to give the false impression that places that have very high fire danger are safe to live in, because it would be unethical to just kick people out of their homes or potentially to remove insurance from them starting tomorrow. We've got a real problem on our hands that goes far beyond understanding the science of wildfire, but we need to begin understanding the societal, the complicated societal relationship we have with fire, and thinking not about what just to do tomorrow, but how we're going to handle this increasing wildfire problem in the coming decades. And with that, I would be happy to take some questions.
Thank you, Park, for such a great presentation, especially for those final thoughts. I think it gave a lot of us a lot to think about, a lot of the researchers in the virtual room. We have quite a bit of questions. I'll try to get through as many as I can with the time that we have, and whatever we don't answer at this time, we'll move them over to the discussion. So there's a couple questions here from Eric. They ask, Is there an agency or organization that tracks the root cause by wildfire in the US? If so, where can that be found? And then they clarify, does someone track root causes of wildfire ignition?
Yes, like I said, the data set isn't that long, but the data set that I'm familiar with that does this is provided by Karen Short of the U.S. Forest Service. And that data set has been published. The published version of the data set covers 1992 to 2010. You can find that at this link here, or you can just simply search Karen Short wildfire data and you'll find it. Karen Short has updated that data set through 2017 though, and she shared the data set for me or with me, allowing me to use it for presentations like this one. But I don't think it's yet publicly available. But this data set contains actually, I think, a couple million fires in the Western United States, fires as small as 0.1 acres. And with each of those fires, the cause of the fire is provided, such as lightning, or even things as specific as children playing.
Thank you. All right, and then we have a brief question, and they ask, is air temperature a driver?
It seems very difficult to get around the conclusion that air temperature is an important driver of area burned. So just here on this left plot, we're looking at the vapor pressure deficit as the predictive variable of burned area, but temperature is really the driver of vapor pressure deficit. As you warm up the air, then you dry it out. You essentially increase the sponginess of the atmosphere as you warm it up. And that causes vegetation, ecosystems, and dead fuels like pine needles on the ground to dry out. And dry fuel burns more easily than wet fuel. So certainly there's a relationship between these two variables, and temperature is at play. And so it makes logical sense that as we increase temperatures, then we should expect ecosystems to become more flammable as a result. The complication just arises in trying to figure out how important it is, because this temperature-related variable, vapor pressure deficit, is strongly correlated with other things that are also certainly important to wildfire, such as precipitation.
Great, thank you. I think we have time for one last question before we move on, maybe two. So this question asks, they say, does area or acres burned since =84 really tell an accurate story of the change of fires, since there has been so many changes in wildfires or present policy changes? And they list quite a bit of different initiatives, from the 2001 National Fire Plan to the 2009 Flame Act and the 2014 Cohesive Strategy. And they follow up saying, or asking, is acres alone sufficient to suggest poor management, policy, lost control of the West, when these acres might have been allowed to burn beneficially?
Okay, that's a lot of good questions. I'll try and hit them all, but apologies if I forget or just run out of time. No, 4 decades is not ideal to understand the full climate, vegetation, fire relationship, but this is the time period when we have really good data. 1984 was selected as the beginning of the study period because that's when our really high resolution satellite records of area burned began, allowing us to do really precise calculations and comparisons of area burned to climate. But we know that over the long term that there have been much larger changes. Prior to large-scale interference by suppression, annual acreage burned was on average much larger than it was during the last 40 years. And so this increase that we've seen in the last 40 years in burned area could be thought of as partly a return toward toward what might be thought of as a more natural annual acreage burned. The problem is that we've been trying to prevent that this entire time. It's not like we've just put up our hands and said, fire suppression was not a sustainable practice. We're going to stop suppression, and then we're just seeing a natural rebound of burned areas. We're still trying essentially as hard as we can. And so there were some specific policy decisions that were mentioned in this question, asking about those, and really bringing up the important point that during this study period, policy has changed. In some places, we actually have been allowing some fires to burn more naturally. In some places, we've been trying to do more prescribed burn on landscape or mechanical thinning, and all of that, or much of that, has occurred during the study period. What this plot is showing on the left, though, is that any effects that those policy changes have had are kind of not really coming through at the scale of the entire Western United States forest area. They've certainly had influences on individual fires or in specific subregions, but we see that at the end of the day, climate has really been the dominant driver of how much area is burned in a given year or how much area is burned in a given decade. Finally, no, acreage burned is not the ideal single measure of fire activity, even though I've used it as a single measure of fire activity in this talk. There are definitely such things as good fire and bad fire. And in some areas, ecosystems or people are not, can respond positively to a low intensity fire, but negatively to a high intensity fire. That's not true everywhere. High intensity fire is important for some ecosystems. So fire intensity and severity are also really important, and I don't touch on that too much in this analysis.
Great, thank you. Well, thank you for answering that last question. We are unfortunately all out of time, but we do have more time to discuss the rest of these questions and new questions that might arise. Before we move on, please join me in virtually thanking our speaker for their time in joining us this week and giving this great presentation.
Yeah, thanks everybody for joining, and I was really happy at the end of the talk to find out that I wasn't on mute the whole time.
Thank you, everyone. We have the discussion link right on the Zoom. If you can't find it, let us know. I'll see you soon. All right, and I'll be